This is the Master Brewers Podcast, brought to you by the Master Brewers Association of the Americas, a volunteer organization dedicated to continually improving the products and processes of our membership since 1887.
Let's go!
Master Brewers brings you interviews with the industry's best and brightest in brewing science, technology, and operations.
Calm down, I'm moving too fast.
This Master Brewers podcast is proudly sponsored by Barnett Mechanical, a full-service design build firm specializing in turnkey process and utility systems for the brewing industry. You know beer. We know breweries.
Additional support provided by
Draft Lab knows that quality and consistency are your brewery's top priorities. Draft Lab provides easy-to-use sensory analysis tools designed to bring your tasting data into action. To start your free 2-week trial today, visit draftlab.com. That's DRAUGHT lab.com.
That the beer yeast that are now used in the US were not native to the US, so they're not isolated from the wild and then used for brewing. They were actually imported by English settlers.
This week on the show, the Yeasts of Tomorrow from one of the most advanced yeast labs in the world.
Hi, my name is Stijn Mertens. I'm working at the University of Leuven, doing my PhD, but also am the master brewer of our pilot brewery.
Hi, my name is Steensels. I'm a postdoc in the lab of Kevin Verstrepen, and I'm managing the industrial context that we have.
I want to start off with a question. Why does beer taste so good? And what does the brain of a fruit fly have to do with the answer?
Should I take it? Yeah. So it's an interesting question, right? Brewers are using yeast already for thousands of years to, they didn't know it yet, but they use it to flavor their beer, to make alcohol, but also yeast is one of the main reasons why beer tastes so good. So it produces, besides alcohol and CO2, a lot of these other metabolites, secondary metabolites, which contribute to the flavor of beer. You can think of, for instance, isomyl acetate, which is the best known one, which really contributes to the fruitiness of a beer, like the banana flavor. Interesting enough, so yeast produces this compound, and the compound is exactly the same compound that makes a banana smell like a banana, basically. So we were intrigued, why would yeast do this? Is it just to please the brewers, or is there another reason? And that basically kicked off the whole research into why yeast produces these aroma compounds. Going through that research, we then found out that in wild, yeast also produces this, and it could be a way to basically attract insects to its location. And there's a whole story behind it. And basically, so yeast doesn't have legs or can't move by himself. So when it's growing, for instance, on grapes, it can use the sugars in the grapes, can ferment these sugars, lives very happy. But then when he runs out of nutrients and sugars, he has to move from one place to another. And because he can't do it himself, he needs to attract something to move from one position to the other. And that could be by attracting insects. And then we basically, in this paper that we published a couple of years ago, showed that indeed these fruity aroma compounds that yeast produces attracts insects. And so we showed that indeed a yeast that produces a lot of these compounds get attracted more than a yeast that doesn't that attracts more insects than a yeast that doesn't produce these compounds. And it also really, the insects react to these compounds and really are attracted to it.
So what inspired that work? Who made the connection between fruit flies and yeast?
Yeah, so basically the project was started by my professor, Kevin Verstrepen, a while ago during his own PhD. So he was looking into specific genes in yeast that make a yeast produce these aroma compounds. And the interesting thing was he made some strains that didn't produce these compounds anymore and strains that produced a lot of these compounds. He was doing testing in the lab. It was Friday afternoon. And instead of cleaning up his bench, he just left it and went off to drink a beer because the weather was nice. When he came back on Monday in the lab, he saw that some of his bottles with his yeast had a lot of fruit flies in it, because next door there was a fruit lab working with fruit flies. And some bottles had a lot of these flies, some didn't. And it was the case that the one that didn't produce these fruity compounds didn't have any flies, whereas the one that produced a lot of these aroma compounds was infested with fruit flies. And that sparked the whole project, basically. So, it seems that these flies are attracted to it. And then we start digging into the why and how.
That's very good. And did that lab next door, are they the ones that helped you kind of look into the brain of a fruit fly, or how did that work?
So that was quite some time later. So we worked with specialized other labs who really study fruit flies and are able to make these, really look into the brains, let's say, of fruit flies and look to neural responses. So that was another lab.
All right, very interesting. Your lab does things with yeast that most brewers probably don't even realize are possible. Could you give listeners some background about your lab? Where is it and what happens there?
So we're a lab at the University of Leuven. So we're situated in Belgium. Our lab is led by Professor Kevin Verstrepen. We only work with yeast in our lab, and we basically have two topics that we tackle. So we do a lot of fundamental research where we use yeast as a model organism to study eukaryotic diseases. I'm just thinking about the Huntington's disease, cancer, and all that stuff. But on the other side, we're also doing a lot of more applied research where we use yeast, basically. Not really use yeast, but let's say that we look into the fermentation capacity of yeast, and that we look at applications as winemaking, sake production, but of course a lot of beer research that we do here. And there we always try to make the process more efficient, so faster fermentation, high gravity, and so on. Or we try to diversify the end product by having other aromas produced by the yeast.
One of the areas your lab focuses on is exploring the natural diversity of yeast. Tell us more about that.
So the interesting part about our lab is that we have a very broad yeast collection. It's an historical collection that we inherited from the university, and it comprises of thousands of different yeasts coming from different industries from all over the world. So we have, a lot of brewing yeast, but also sake yeast, yeast that is used in winemaking, and so on and so forth. And what we do is we, first of all, try to phenotype them as good as possible. So we try to characterize and see how well they behave in different fermentations, which aroma compounds they make, and so on and so forth, just naturally out there in these. And we also look into their genome, and we look into how well they are related to each other. So which yeast are nephews or nieces, or are even closer related. And there is a lot of information that makes our lab special, because we're a lab, one of the few labs with such a yeast collection, and that is that diverse, but also so well characterized. So just looking at what is out there already in nature allows us to already select some interesting strains that brewers might not know of for their application.
Your lab does so much screening that it has to use a robot. Tell us about that.
Indeed. So we're very happy because we have a very we have a lot of robotics, but one of our robots is the plating robot from Singer, which basically allows us to handle about 100 strains in parallel, whereas we used to use a lot of thesis students to do this. All the pipetting stuff is now happens basically with robotics, so you can screen easily 100 different strains for 20 and more phenotypes in one go, in one experiment.
That's amazing. Do you want to talk about some of the biodiversity of brewers' yeast that you've managed to observe and characterize?
So this is maybe really a question for Jan, because that was, he was one of the main authors on that publication. Mm-hmm.
So like Stijn said, we really looked into the genomes of the different beer yeast. And often when people do or did genome analyses of yeast, they often neglected the beer yeast for the simple reason because they're extremely complex. So normal yeast have a relatively simple genome, something that we call diploid, so 2 copies of each chromosome, while for beer yeast it's much more messy. They often have 3 or 4 copies of each chromosome. And a lot of aneuploidies, meaning that they're missing or having duplicated chromosomes. So there wasn't a lot known about the genomics of beer yeast. So what we did, we sequenced a bit over 100 beer yeast, I think, and we saw several things, but I guess the main conclusion was that we can separate the current biodiversity of beer yeast in 2 distinct groups, which we call the beer 1 and beer 2 group. We're not very imaginative. But we see that there are 2 sort of archetypes of beer yeast. And interestingly, one of the 2 beer groups, the biggest one, the beer 1 group, you can also subdivide them in geographically. So you have a clade that is really specific for Belgian and German yeast, so more Western Europe. We have a UK clade, so with all yeast from the UK. And stemming from this UK clade, we also have a clade of the beer yeast of the US. So we were able to show by looking into the genomes, and that was one of the outcomes of the paper, that the beer yeast that are now used in the US were not native to the US, so they're not isolated from the wild and then used for brewing. They were actually imported by English settlers around the time that they got there. So using this genomic information, we could sort of tie it back to some historical facts and tell a bit of history about the diversity of beer yeast that we see today.
And that family tree that you've published is very interesting. It's an incredible visual. Where can folks go to find that?
So we published this in a 2016 paper in the journal called Cell, and we made the paper open access so that anyone can access it. If you go to the lab website, you can easily find it there as well.
Okay, great. I'll include a link to that. Coming up.
But on a genetic level, what we're doing in our lab is basically crossing humans with chickens.
I'm John Bryce, and you're listening to the Master Brewers Podcast from the Master Brewers Association of the Americas. This episode is brought to you by
ABS Commercial is a full-service brewery and parts outfitter. From our Raleigh headquarters to our Denver office, we proudly offer brewhouses and fermenters from 3 barrels and up, yeast brinks, boilers, kegs, chillers, tri-clamp, and other stainless parts, all with the quickest delivery and lead times in the industry. Learn more at abs-commercial.com or call 877-BREW-ABS. ABS Commercial. We are brewers.
Here's what's coming up on the Master Brewers calendar. District Northern California invites you to attend the California Craft Beer Summit September 6th through the 8th in Sacramento. The District Rocky Mountain Summer Meeting is September 7th and 8th in Cheyenne, Wyoming. It may still be summer in Cheyenne. Meanwhile, District Midwest holds its fall meeting September 8th at Fatheads in Middleburg Heights. The Master Brewers Engineering and Utilities course begins September 9th in Madison. Don't miss the keg cleaning and sanitizing webinar September 12th. District Western New York meets at FX Mat in Utica September 13th. The District St. Paul Minneapolis Golf Outing and September meeting is September 14th. The St. Louis Annual Golf Tournament is September 20th. The 2018 District Ontario Iron Brewer is September 28th. And District Southern California meets in San Diego September 29th. View the full calendar of events at MBAA.com for more details or to find a district meeting near you. Now back to the show. And sometimes you've found strains from other industries or applications that ended up working well for beer too, right?
Yeah, that's true. That's true. Because I mean, the thing about beer yeast is that a lot of brewers are very attached to their yeast. I mean, they have it for generations, for centuries, sometimes even, and they really build their whole process around that particular yeast. And yeast might not be optimal yet, and they really might need to have suboptimal solutions in their process design in order to make the yeast work. But if you would go a bit broader and look into different yeasts, and not necessarily yeasts that are now used in beer production, you can easily find strains that do as well or even a bit better than the yeasts that are around now. And this is especially true for sort of new processes, for example, high gravity brewing, in which you need to reach very high ethanol concentrations, continuous beer fermentations or fermentation or beer fermentation in which you want to reach very high aroma levels and so on. So for these very specific applications, there are most definitely yeast out there which might be better than the current yeast that are being used. But yeah, brewers are very often very reluctant to change their yeast because they're so used to it.
Stijn, you have some interesting observations regarding the domestication of beer yeast versus wine yeast. Talk about that.
Yeah, so interesting, there are indeed some characteristics that beer yeast retained in their genome, whereas wine yeast don't have it anymore. There are definitely differences there. So, for instance, one of the major things we saw is that the wine yeast are often not able to use maltodextrose and maltose, which are the main carbon sources or sugars in the brewer's wort, whereas beer yeast obviously can use these sugars. So if you would use those wine yeasts which can't use these sugars, for beer brewing, you will have less ethanol, more rest sugars, so you have a very sweet beer. Another thing that it was very striking is that, and that's very specific for the beer yeast, is that they lost the ability to produce phenolic off flavors. Phenolic off flavors or POF flavors, for instance, the best known is 4VG, 4-vinyl guaiacol, which adds the clove-like off flavor, which you really can still taste in wheat beers, for instance, Belgian wheat beers or the German Weissen beers. So this is often not wanted in most of the other beer styles. And it seems that all the brewing yeast, or almost all of them except the ones used for these wheat beers and Weissen beers, lost this phenotype. And if you then look to the POF characteristics of all the other yeast, wine yeast, but also other yeast, they all still retained it. So it seems that indeed the brewing yeast was really domesticated for brewing beers, for the use in the brewery.
So, if I may, I want to add one more thing to this. Is that if one of the main differences between the beer and the wine yeast, or the beer and the wine production process in general, is the way that the process is being done. Beer is being produced continuously, so the yeast are continuously present in this beer medium, and people used to and are still serially repitching their yeast, so they're continuously growing in beer wort. While for wine production is seasonal, so after the wine is being produced, the yeast must go back to nature and be able to survive also outside this wine environment. And this is very well reflected in the genomes and the phenotypes of the yeast as well, because the beer yeasts are really very, very specifically adapted to this beer environment, while and cannot really survive on the outside. They're very poor in surviving sort of natural stressors and that kind of stuff. But the wine yeasts are more robust. They can you can leave them in the vineyard over winter and they will survive. And the way that the analogy that we often use is that beer yeasts are then a bit more like dogs, who really need the company of humans, while wine yeasts are a bit more like cats. You can sort of drop them in the wild and I'm pretty sure they will be able to survive. So this I think is a good analogy to see the difference between the beer and the wine yeast.
Breeding superior variants is an area of focus in your lab. Tell us how that works. While you don't have to wait 15 years like a barley breeder, there must be a unique set of challenges.
So yes, indeed. So breeding yeast is challenging for a couple of reasons. So first of all, yeast cells are very small. You can't really see them with the naked eye, so you need special equipment to start breeding different yeasts with each other. Whereas, of course, when you work, for instance, with cows or plants, you just take two plants or a cow and a bull, put them together, and you see them actually mating. So in that sense, you need special equipment, and that's why I would say we have. We're not doing it already for thousands of years, and that yeast breeding is something very recent. On the other hand, so breeding yeasts, the other challenge is that you need to exploit their sexual life cycle. So yeast is very special in that. So it can reproduce itself by clonal budding, it's called, or it can form spores. And you need this formation of spores to be able to cross different spores of different yeast, which often is very tricky for a lot of industrial yeast. But we optimize the protocols so we can actually now do this in our lab with a high efficiency. And then it's indeed a case of selecting two interesting parental strains. For instance, if you want to have a high alcohol beer with a lot of aroma, well, if you don't have the best strain already out there, we'll select a very aromatic strain, cross it with a very robust strain that can produce a lot of alcohol, and then hope that we have segregants that combine these characteristics of both parental strains. And then to come back to your remark that indeed it doesn't take as long as for plant breeding, indeed the sexual cycle of yeast is only a couple of, not sexual, but it can reproduce itself in a couple of hours, whereas indeed for plants it takes weeks and years to get this going.
And one additional advantage that I want to add for yeast is that you can literally make like a couple of million new hybrids in a small tube. So the scale at which you can do breeding is much, much bigger. And of course, I mean, power is in the numbers. So if you can make more hybrids, you have a bigger chance of getting superior ones. So there are two things that yeast has going in terms of breeding, but there are also a few more technical downsides, I would say.
Definitely need more robots too, right?
Yeah, that is true, yeah.
Okay. Well, is it safe to assume you guys have seen the movie Napoleon Dynamite?
I've seen it, but it's been a decade, I think. So
Sure. Well, I can't resist the opportunity to talk about the liger, which is pretty much my favorite animal. Tell us about your work related to crossing species borders to make the ligers and zonkies of yeast.
So yeah, it all started off when we wanted to make new lager yeast. So lager beer, which accounts for 90% of the worldwide beer production, is basically fermented with a different yeast species than ale beers. So ale beers are produced with Saccharomyces cerevisiae, whereas lager beers are produced with Saccharomyces pastorianus. And the interesting about this yeast is actually that it is what we call interspecific hybrid, like the lagers, meaning that is the result of crossing two different species. So it is, on one hand, the ale yeast Saccharomyces cerevisiae, which we all use to produce our ale beers, and on the other hand, a cold-tolerant contaminant called Saccharomyces eubayanus. And so the interesting is, so Saccharomyces pastorianus is this type of interspecific hybrid. But if you look into the genome of the lager yeast used across the world, they're all very similar. So there basically are only two archetypes. They're called Saas and Froberg. And within those groups, diversity is very limited. So what we try to do in our lab is to recreate this event. Let's try to cross different yeast species. So not humans with humans, let's say, but on a genetic level, what we're doing in our lab is basically crossing humans with chickens. So we cross different cerevisiae strains with interesting properties with different, with other species like Saccharomyces eubayanus, Saccharomyces micata, and so on and so forth. So we try to combine characteristics from two different species in one organism.
Very cool. And with all this work that you do, I think screening is really sort of going to always be your bottleneck, even with robots. Talk about the lab-on-chip technology and how you're using that.
So we already talked about our robot. So what we're doing now is screening hundreds to thousands in parallel on plates, 96 well plates in small fermentations. But indeed, if you cross two different strains, for instance, you get 1 million of offsprings. You can't do this for all of these offspring. So we were looking to a way to miniaturize our assays and to increase the throughput of our screenings. And for that, we started collaborating with a company who is next door, who basically develops microchips. And we started to make what we call a brewery on a chip. So what we can do there is encapsulate single cells, yeast cells, in micro droplets. And we fill them with wort or other media. We have them grow, and then the idea is that we, in the end, with enzymatic assays, can screen different metabolites they form. For instance, which sugars they use during the growth in these small droplets. And then we designed a sorter, which allows us to basically select the top few out of these millions of cells with these enzymatic assays then.
Before we wrap up, I want to talk about your new book. What can you tell us about it?
So we started making a book about Belgian beer, and the main reason was that we have a huge diversity in Belgian beer. So we have all these different beer styles, different beers. We have more than 1,000 to 2,000 different beers in our small country being made, and we wanted to have like an objective view on the diversity of Belgian beers. And for that, we selected a set of 250 different beers coming from all the different Belgian beer styles, and did a whole chemical and sensorial analysis on them. What we did is we measured more than 250 phenotypes of all the different beers, and then also, of course, had them tasted by a trained panel. And we combined all this data in a book. So in a way, what we made is a roadmap, or a roadmap, I would call it, of the Belgian beers. So you can see where a particular beer of interest is positioned among all the different beers, what beers are similar or not, and if you like a beer, you can also see what basically characterizes beer, what is very typical for this beer chemically, but also sensorial. So we hope that people will use it as a tool to basically discover Belgian beer, or just beer diversity in general. Or even, for instance, for home brewers, it's very interesting if they want to make a beer very close to a particular known beer. They can look, okay, which parameters do I need to go for in my beer?
So if I may, John, I want to add one more thing about the beer book.
Please do.
So, and this is maybe the only new thing that we can tell during this talk, is that we have now this big data on a lot of beers, a lot of chemical data, a lot of sensorial data. But one huge thing that's always missing in beer research in general is the link between the two, like the link between the chemical composition of a beer and the way that it's sensorially perceived. So what we're doing now, using machine learning techniques, is we're trying to link the two. So actually develop sort of an electronic nose to predict how a certain beer is going to be perceived. And the output that we hope to get from this is for example, that we could do recipe development and predict how the beer in the end would actually taste. So that's one of the things that we're still. That's one of the follow-ups that we have on the beer book, or on the data that we gathered for the beer book.
That was Stijn Mertens and Jan Steensels here on the Master Brewers podcast. If you'd like to see Stijn's presentation from the 2018 Eastern Technical Conference, head on over to the District Presentations Archive or type Yeasts of Tomorrow into the industry's best search bar at MBAA.com.
Calm down, I'm moving too fast. And then I fall on the ground, just like that one day, like everyone else did. Calm down, I'm moving too fast. And then I hit on the ground, just like